In this video, I will be explaining the Runge Kutta methods, which are numerical methods to solve ordinary differential equations. So the Runge Kutta methods are a generalization of the two previously discussed methods. So we've so far discussed Euler's method and Hoyne's method, which are examples of lower order Runge Kutta methods. So again, we've already seen this expression a number of times. It can be cast in this general form, iterative form, where you calculate a value of y I plus 1 from a value of y I and from an estimate of the slope v times h. So, like I said, v can be interpreted as the representative slope over the interval, and h obviously is the step size, and v is a function of this following form, where v is a1 times k1 is a2 times k2, and so forth. And here the a's are constants, whereas the k's are functions of x and y. And the k's are given by these expressions. So k1 is just the function of f evaluated at xy and yi. So k2 is the function evaluated at xi plus some constant p1 times h, and yi plus another constant q11 times k1 times h. And you can continue this process all the way up until kn. And as you can see, this is a recursive computation. So you can see that that k1 appears in the expression for k2, and k2 in turn again appears in the expression for k3, and it goes on like that. And again, such a recursive nature makes such a method very attractive to use in computer programs. Yes, like I said, there are recurrence relationships, and we can construct different types of Runge Kutta methods, and they differ in terms, in the number of terms that you use in the function phi, which is specified by n. And we'll go over some of the examples in a bit. And once you have chosen a value for n, values for the constants a, p, and q are obtained by equating this expression to a particular form of the Taylor series. And I will not be doing this, I will just be giving the constants for the methods that we will discuss. And the truncation error in a particular type of Runge Kutta method depends on the number of terms that were used in this function phi, and usually the more numbers you use, or the more terms you use, you obtain more accurate approximations. So, like I said, Euler's and Hoyne's methods were examples of lower order Runge Kutta methods. So the first order Runge Kutta methods, so for n is 1, so Euler's method is an example of a first order Runge Kutta method, where for Euler you take the constant a1 to be 1, and your function k1 is just equal to x, to this function of xi and yi. For Hoyne's method, that is an example of a second order Runge Kutta method with these following non-zero constants, where a1 and a2 are equal to 1 over 2, p1 and q11 are equal to 1, and then we get these values of k1 and k2, and if we plug that in, we obtain this expression for yi plus 1. And if we plug in the values for k1 and k2, we indeed see that we obtain Hoyne's method. So the most commonly used, the most popular Runge Kutta method is a fourth order Runge Kutta method. And yeah, it's also referred to as the classical Runge Kutta method, or classical fourth order Runge Kutta method. And it has this following form. So you can see that because it's a fourth order method, we have these four terms in our function for phi. So we have k1, k2, k3, and k4. And these values are given in this with these expressions. So k1 is just f of xi and yi. Then k2 and k3 are these functions evaluated at intermediate points in the interval. And k4 is the function evaluated at the end point of the interval. So you can see it is depicted graphically here in this figure. So, like I said, k1 is calculated from the beginning of the interval. In this case, instead of x, we will use t. And using k1, we calculate k2 at some intermediate point in the interval. And now we again use k2 to improve this solution at the intermediate point to calculate k3. And then finally we calculate k4 at the end point of the interval. So the error in the fourth order Runge Kutta method, so over one single step, you will have a local truncation error that depends on h to the power of 5. So again, we can apply this method, the Runge Kutta method, over a number of intervals. And if we do that, we just sum the local truncation errors for each interval. And then we obtain the global truncation error, which will depend on h to the 4th. So now I will discuss an example where we apply the Runge Kutta method. So now consider this following first order differential equation, where it is again an initial value problem. So we are given the value of y at t is 0 to be equal to 1. And now we want to use this fourth order Runge Kutta method to obtain a solution for y on this domain from t to 0 to 3 with step size h is 0.5. Yeah, so we have these values of y0, t0, and h, and this function f of t and y. And then we will use the initial values to calculate y1. And for that, we first need to calculate the 4 k's. So you can see that we have done that here. So we just substitute the values of t0 and y0 in the function f to obtain k1. And then we use this value of k1, we substitute that into the expression for k2 to get the value for k2. And in such way we can calculate y1, which is given in the last row of the slide, where we've calculated y1 to be 0.4089. So we can repeat this process for each step on this domain, so that we get these values of y for each t, which differ in step size is 0.5. And we use MATLAB for this again, and we can plot it, which is also presented in this figure. So we have this exact solution to the differential equation, which is plotted in blue, and then our Runge Kutta method. And we see that it approximates the solution quite well. We can also solve the differential equation using the previous two methods that we discussed in the previous videos. This can solve it using Euler and Hoynes method as well. And that's what we did in MATLAB, and which is presented in this figure. So again, you have the exact solution given in black. And now we have three estimated solutions. The Euler one in blue, Hoynes method in red, and the fourth order Runge-Kutta method in green. And all three methods have used a step size of 0.5. And indeed, you can see what we would have expected, that the fourth order Runge-Kutta method approximates the exact solution the closest, because the error term, like we saw, is the lowest. So, to recap the ordinary differential equations, we have looked at three different methods to solve initial value problems numerically: Euler's method, Hoynes method, and the classical fourth order Runge-Kutta method. We saw that the global truncation error of these methods were dependent on h squared, and on h to the fourth, respectively. Euler's method was the simplest method, easy to understand. Programming effort is also easy. However, it is the least accurate. That is the trade-off. But still, it might be useful for quick estimates. However, the fourth order Runge-Kutta method, because of its accuracy, is really the most widely used method.